Hello, during this session I'm going to be talking about star death and the elements around us. I guess I'm going to be asking the question, are we all made of stars? Moby, the music artist who we can see his remixes of his song We're All Made of Stars, seems to think so, and I'm going to put some science behind that now. So let's start off with what we're going to think about is nuclear synthesis off the main sequence. So stars run out of hydrogen fuel, that's the end of the time list on the main sequence, and they expand to red giants in an attempt to ignite heavier elements and start nuclear synthesis. So that's the production of heavier nucleuses. We've spoken about that beforehand, there's nothing new there, and this progress is dependent on the initial mass of the star. So the larger the mass, the heavier the nuclear that can be produced. And we know that there's certain limits that get to the points where the stars don't produce any more heavier elements. Seems all fair enough. So we can see in the thermonuclear energy generation of stars, what happens is that a star of approximate mass of 0.1 can burn hydrogen. That's pretty much it. As the stars get bigger, they can produce heavier and heavier elements. So we see a star which is slightly bigger than our sun. Our sun will probably end up producing carbon, maybe oxygen. Then we can get a star which is slightly bigger, and that can actually burn carbon and produce oxygen and neon and sodium and magnesium. And then as we go further up, we can see really massive stars, 20 times, can producing silicon. The fuel being magnesium to sulfur, and elements near to iron are the major products. And we know iron is the end of that cycle. So we're over there going, okay, so all of these elements can be made in the death stages of a star. That's true, but we know there's a lot of elements beyond that of iron. So here we have a red giant onion, or maybe a red supergiant, and we can see at its core we can have some iron, but nothing heavier. It's interesting. So we could be made of carbon. That's fine. Carbon is produced by stars. But what about these other elements? So where do these other elements come from? Here's a periodic table, and the periodic table shows where elements are made. Okay, hydrogen, helium constructed in the Big Bang. Lithium, beryllium, boron can be created due to the interaction of cosmic rays and hydrogen, helium. And then we start seeing that large stars and small stars obviously producing carbon, neon and oxygen, nitrogen and sulfur. Large stars can go beyond that, and we can get up to the production of iron. Now there's a lot of elements beyond iron which can be made by large stars. So let's first about thinking about how is this possible. Well, there's a process, and the process is known as the S process, which actually stands for the slow neutron capture process, the slow process. So over a long period of time, in a large star's lifetime, what happens is slowly neutrons can be captured by elements, and therefore they will slowly manage to get more massive. So here we've got an example of some of the sequences which can take place, and there's lots of sequences. Beryllium is captured by a neutron, so beryllium-209 is captured to produce 210 beryllium, which then decays to 210 palladium by beta decay. The palladium in turn decays, and eventually I have a lead particle produced after there's an alpha decay. So therefore, in large stars, slowly but surely, heavier neutrons can be produced, heavier nucleuses and heavier elements can be produced from this process, and this is known as the slow capture process. So if I just click back, that's the production in large stars. Okay, now that's okay, and we can see everything which says large star in green can be produced by this process. we also see being produced in supernova. Okay, so supernovas are another way. So let's think about that. Supernova 2 type, and these are large stars from 8 to 40 solar masses in size. And the distinction of what a supernova 2 type is actually defined by the presence of hydrogen in the spectrum. Okay, so that means there is some hydrogen left, and we can pick that up in the spectrum. So if that is present in the spectrum we observe of a supernova, it's known as a type 2 type supernova. And this is where the R process of heavier element production takes place. Okay. The R process stands for rapid process. So let me talk about the rapid process now. So what happens with the R process, rather than slowly building up in the high temperatures of a supernova, we get a large neutron flux. So that means lots of neutrons are released because of the various processes that are taking place. And this neutron capture creates very neutron heavy rich isotopes, which in turn decay after the event to create first stable isotopes. And these are the heavier masses elements which we now observe. So these are all the heavier elements which aren't man-made, are created in a very, very rapid process during a supernova. And because of the high temperatures and the abundance of neutrons, this allows this to happen. So we may see a diagram like we see in the diagram here, and what eventually happens is, although there's lots of unstable isotopes produced, we've also got beta plus and beta minus decays taking place. Eventually this process can lead to a point where we can create stable heavy elements. I should also mention the other type of supernova that's observed, supernova 1A. Now, this isn't really about the production of heavier elements, but it's worth mentioning it now because I'm talking about supernovas, and there's a feature of supernovas which is really, really important in looking at the distances to galaxies. We're going to talk about that in a later session though. For now, what happens is when we have a white dwarf formed, yet it's in a binary system. Now, what happens is the white dwarf is formed, but it can accrete, so it can suck off gas and matter from the partner star. And because it increases in mass, it will cross over what I've mentioned before is the Chandrasekhar limit, which is 1.4 times the mass of our Sun. And when it gets past that point, it can ignite carbon. So there's been carbon there, and that we thought was the end of the situation. But in this case, because there's extra mass, it allows it to push it, so it ignites carbon fusion. Nothing more but carbon fusion. And that causes an explosion. And this explosion has a very, very, very consistent luminosity, which allows us to be able to use it for calculating distances to distant galaxies, where we can observe the supernova standing out from the rest of the light of the stars. And as I said, this one's interesting because it will not have any hydrogen in its emission spectrum. So there we go. There's an overview of how the elements are produced after the death of the star, and how we can confidently say that we're all made of stars, and all the heavier elements around us are made of stars as well.